we'll get started. And this morning we will start with a session on entanglement witness. I'm Scheie from Rice University, and we have three invited speakers. We'll start off with Alan Scheie from Los Alamos. Alan, what is yours?
All right, well, thank you very much. I want to thank the organizers for putting together what was a really great workshop yesterday. I'm looking forward to today. And for giving me the invitation to come back to Houston. I lived in Houston until I was 8 years old, and so whenever I come back, it brings back fond memories. So I'm excited to talk about interpreting spectroscopic quantum entanglement witnesses. This is a talk that's kind of a follow-on to some work we've been doing on entanglement witnesses. And here I'll be trying to answer a very specific question. How do we interpret quantum Fisher information in condensed matter? And this is a complex question, but I'll be giving 4 answers to it. And let me begin with these 4 answers so that you know where I'm going in this talk. First, QFI, quantum Fisher information, measures the degree of quantum superposition in the state that you're measuring. Second, the Q dependence or momentum dependence of QFI carries information. Third, semi-classical models can show very large, even diverging quantum entanglement. And fourth, diverging entanglement signals instabilities and emergent quantum phases. And by the end of the talk, I hope you understand what I mean by each of these things. All right, so let's begin with something very basic, especially since we're waiting for the shuttle to arrive. In 1935, after a series of very public debates with Niels Bohr, Albert Einstein and his co-authors published this EPR thought experiment paper showing that spooky action at a distance is a consequence of quantum theory. The thought experiment is very simple. You have particles A and B that interact, and then you separate them by a large distance, and then you cannot measure incompatible observables simultaneously. Later that year, Erwin Schrödinger wrote a letter to Albert Einstein congratulating him on this paper, and this is where the word entanglement came from, because Schrödinger coined this term to describe when 2 bodies cannot be described independently of each other. And for the next few decades, this was kind of considered a philosophical issue in quantum physics until 1964, when this man, John Stuart Bell, realized that there are actual experimental consequences of quantum entanglement. And he followed up on the EPR thought experiment, proposing something very similar. Imagine you have 2 spins that are quantum entangled, and they form a singlet state, a superposition of up-down and down-up. And Bell imagined what would happen if you could measure the spin polarization of these 2 spins and rotate your polarizers at an arbitrary angle phi with respect to each other. Well, if you sit down and you calculate the 2-point spin correlation function, S dot S, you find that there's a difference between the classical unentangled case and the quantum entangled case. The classical case follows a linear dependence on the angle phi. The quantum case follows a cosine dependence. And this is an experimental difference that can be measured in principle. So it took some years, but this eventually was measured. The key measurement came in 1981 when Aspect and his collaborators measured this cosine dependence and found that the Bell's inequality was violated by 9 standard deviations. And this and other experiments were awarded the Nobel Prize in Physics 3 years ago. Now, I bring all this up because I think there's 2 important lessons for us from John Stuart Bell's work. First, quantum entanglement can be witnessed experimentally. There are experimental signatures of quantum entanglement. And second, quantum information is embedded in 2-point correlation functions. This was the foundation of Bell's work. And so now we come to the motivating question for my work is, can we measure quantum entanglement in solid materials where we have Avogadro's number of electrons? Now, in the solid state, we can't measure and manipulate individual electrons. So doing a direct reproduction of Bell's sort of experiment is out. We have to find a different route. But we can take inspiration from John Stuart Bell's work in realizing that the 2-point or 2-spin correlation functions embed information about entanglement. This is what's measured in a Bell test, and this is also what's measured in a neutron spectroscopy experiment. Because if you look at the equation for the magnetic neutron scattering, what is measured is actually a quantum 2-point correlation function, Fourier transformed in space and time. What this means is that entanglement information is encoded in the neutron structure factor. The trick is knowing how to extract it. So let me go to part 2 of this talk, where I'm going to introduce these spectroscopic entanglement witnesses. So this is something I've been working on for the last 5 years or so in collaboration with Pontus Laurel at University of Missouri and Alan Tennant, who's at University of Tennessee. And we recently published 2 reviews on this topic. This first review is more of a theorist review that has derivations of all the equations. The second one is more of a pedagogical tutorial with experimental considerations and interpretation. And I encourage you to look at these if you're interested. But of all the entanglement witnesses we've tried, and there's a whole family of them, the most robust and easiest to do by far is called quantum Fisher information. And this is important for the rest of the talk, so I'm going to give a few technical slides so we can formally define what I mean. Quantum Fisher information is borrowed from the quantum metrology community, and it defines how precisely an operator O can be measured. And for a pure state, the equation is very simple. It's simply 4 times the quantum variance of this observable. Now you ask, why does this matter? Well, this becomes really important because by something called the Cramér-Rao bound, this quantity gives you a lower bound on the number of entangled objects, such that if your f of q becomes very big, this requires more and more degrees of freedom to be entangled. And there's this specific inequality where f of q is greater than m, where m is an integer, times the difference in the maximal and minimal eigenvalues of your operator squared. And this m quantity gives your entanglement depth, such that, or multipartite entanglement, such that if you measure m, then your system is at least m plus 1 partite entangled. Now, I want to emphasize this equation is very generic. You can define your operator O to be whatever you want. So if you wanted to define your operator as a rubber duck operator, you could measure the quantum Fisher information of rubber ducks in your material, as long as your ducks are Hermitian. But the intelligent thing to do for neutron spectroscopy is to define your operator as this S of Q operator right here, which is a Fourier transform of your spins along a given spatial direction modulated by this wave vector Q. When you do this, the equation for quantum Fisher information looks like this at the bottom. And those of you who are familiar with neutron spectroscopy will notice that the term on the left is equal to the total or energy integrated scattering at a given wave vector Q. The term on the right is equal to the elastic or omega equals 0 scattering at a given wave vector Q. And both of these are experimentally measurable. If you energy resolve your neutron scattering experiment, you have access to this quantity. Now, all of this was for a pure state, which is only valid in the 0 temperature limit. Real experiments are always done at some finite temperature. And so a key breakthrough was provided in 2016 by Peter Zola and HOQE. They published this paper in Nature Physics where they began with the thermal state definition of a quantum Fisher information, and they derived this equation, giving quantum Fisher information at finite temperature as an energy integral over dynamic susceptibility weighted by this hyperbolic tangent function. And you can see that in the 0 temperature limit, this hyperbolic tangent becomes a step function, and you recover the original equation as it's integrating over all inelastic scattering, but excluding the elastic line. Okay, so the important thing I wanted you to remember from all this derivation is that quantum Fisher information gives you a lower bound on the number of entangled spins and is measurable with neutron scattering, such that if your system has this NQFI, which is our normalized quantum Fisher information by the spin length squared, if this is greater than m, your system is m plus 1 partite entangled. Right, so about 5 years ago, we did the first quantitative experimental test of this theory. We tested it on a 1D spin chain, potassium, copper, fluorine 3. We picked this because 1D is very well understood. We can simulate it very accurately with DMRG. And we saw that there's a really excellent overlap between theory and experiment, and we're witnessing at least 4 partite entanglement at low temperatures. Since then, we've gone on to apply this to many different materials. For example, the 2D triangular lattice, potassium, ytterbium, selenium 2, the spin 1 nickel honeycomb material, NIPS3, and a copper dimer system as well. So we've shown that it works. You can get this information from neutron scattering. But the real question, the most important question, I think, is what does this really tell us? And this is what I'm going to focus on for the rest of this talk. Because in condensed matter, people don't normally define phases of matter by their entanglement depth or multipartite entanglement. So we have to kind of translate what we're getting here into the sort of quantities that we as condensed matter physicists really care about. So to try to answer this question, I want to focus on some very simple examples so we can build some intuition. Looking at first some finite size spin chains, and second, some semi-classical models. Now let me begin by sharpening this question to something a little more specific. What does QFI actually probe? Yes, it's related with an inequality to entanglement depth, but what does QFI, the quantity, actually mean? And the answer, when you consider some very simple systems, it becomes clear. You're measuring the degree of quantum superposition in your ground state. So let's consider an example of a spin chain of 8 spins. And if we begin with a very simple state, a uniform ferromagnet, all the spins polarized, and no different kets in superposition with each other, the QFI you can calculate, you find that this equation, this term in the equation, and this term in the equation are equal. And so QFI equals 0. This is a very strongly correlated state. Every spin is correlated with its neighbor very strongly, but there's no entanglement. And in fact, any ket that you write down, it doesn't matter the pattern of spins, as long as there's no superposition, QFI will equal 0. However, as soon as you, yeah, it will. Give me a few slides and I'll address that question because that's really important. Right, you note that here I'm putting in q equals pi. You could also put q equals 0 here and still get 0. But as soon as I add some degree of superposition, where here in red I've denoted the spins that are in some opposing state of superposition between the two kets in the ground state, then you start to see some non-zero QFI. And as your superposition expands through your system, your QFI grows such that when every spin is in a state of superposition, then your QFI equals the number of spins in your system. And you can generalize this from very small systems all the way up to arbitrarily large system sizes. You can define a Schrodinger cat state of n spins. And as long as every state is in a superposition, then you get n-partite entanglement. So what this is demonstrating is that QFI is really measuring the degree of superposition in your ground state. But now I want to get on to the question that was just posed. What does the Q dependence, or the momentum dependence of QFI mean? And this turns out to be a very complicated question that has lots of subtleties. Here I'm going to provide 3 answers to this question that, at least in our work, we've found to be useful ways to interpret this. The first answer is that the momentum which maximizes your quantum Fisher information gives you the most rigorous and stringent bound on multipartite entanglement. So consider, for example, a single spin floating in free space that's just a superposition of up and down. There's no momentum dependence because there's nothing to be correlated or entangled with. And so QFI and QFI is precisely 1 at all momenta, meaning the entanglement depth is 1 and you have no entanglement. But consider an antiferromagnetic dimer, where in our ground state we have a singlet, up, down, and down, up. In this case, QFI is peaked at q equals pi, the antiferromagnetic wave vector, and it falls off to lower values away from this. And so this is a bipartite entangled system, but to get this maximal value, you have to choose the momentum associated with the antiferromagnetic correlations. Similarly, if we picked a GHZ type state, a ferromagnetic trimer, here we would find QFI equals 3 for tripartite entanglement, but here the QFI is peaked at omega, or Q equals 0, corresponding to ferromagnetic correlations. So the point of this exercise, you pick the Q, which maximizes your QFI, and this gives you the most stringent lower bound on multipartite entanglement. Right, and you can generalize this to any size system you want, going from 2 spins to 4 spins to 6 spins. And these are just, antiferromagnetic singlet type states. And you find that QFI is peaked and equals the number of spins, but only at Q equals pi wave vector. And you can go out all the way to n spins. Sorry. That's right. So this is what we're measuring here is 2-spin correlation functions, but on a system that is growing in size.
Yes, but the other one, for my trimer,
we're still only measuring 2-spin correlation functions, but you do the closed form calculation of what if you have 3 spins that are entangled in the ground state. And this is what comes out.
You should never wear this, right?
No, we're not measuring a 3 scattering. There's nothing wrong with that. But the key thing, like we're only measuring 2-point correlation functions, but looking at system sizes that we can vary arbitrarily. That's this exercise. And in fact, you can do considering the thermodynamic your cat state, but of course, gap between the ground state and the first excited state goes exponentially to 0 as long as you have, and this is why we don't observe quantum superposition in the world around us in the thermodynamic limit. But okay, so the first answer to this question though is important. What does the Q dependence mean? The Q, or the momentum, which maximizes your QFI, gives you the most stringent bound on multipartite entanglement. So that's our first answer. But there's a second answer, which I think is also important. The Q dependence tells us the degree of quantum superposition away from Q equals K, where K is the ordering wave vector or the wave vector of the strongest correlations in your ground state. So here I've plotted the normalized quantum Fisher information from the beta-Ansatz solution to the ground state of the 1D Heisenberg spin chain, which is this very highly entangled non-trivial state. And you can see that the QFI is peaked very strongly at the antiferromagnetic wave vector Q, indicating along this wave vector, we have a very strong entanglement and a large degree of quantum superposition. But as you move away from this, we still have finite values of quantum Fisher information. So if we look, for example, at pi over 2, this is indicating that we have some degree of superposition in the ground state of up, up, down, down, up, up, down, down. And indeed, the ground state wave function includes this in its ground state. And QFI is telling us this in its wave vector dependence. So the second answer, Q dependence, tells us the degree of quantum superposition away from this maximal value of QFI. And a third answer, which is maybe the most intriguing, is the Q dependence of QFI encodes what we are calling a quantum correlation length. Because actually, if you look at the thermal definition of QFI as an energy integral over dynamic susceptibility, weighted by this filter function, depending on what filter function H you choose, you're actually accessing a whole family of information theoretic quantities. If you pick a hyperbolic tangent function, you get QFI, which is what we've been talking about. But if you pick this Langevin function, you access this different quantity called quantum variance. And if your filter function is this crazy equation, you get something called the Wigner-Yancey-Dyson skew information that was proposed by Eugene Wigner back in the 1960s. And they each have slightly different information theoretic definitions that are very precise. But we took this whole family of filter functions and we applied it to our one-dimensional spin chain data as our kind of test case. And we found something interesting, that regardless of what filter function you choose, you get roughly the same spatial dependence. If we calculate the quantum integral versus space, then we get about the same spatial fall off. And this spatial fall off this length scale is qualitatively different than the total correlation length in the system. This is it plotted versus temperature, where the total correlation length is in the dashed and open symbols. The quantum correlation length is in the closed symbols in the bottom. And I think this becomes a bit sharper when we do this on a theoretical simulation. In collaboration with Tommaso Raschilda, we did quantum Monte Carlo on a series of coupled 1D spin chains, where the x-axis gives the coupling between spin chains, the y-axis gives temperature. And you can find that when you're looking at the total correlation length, as long as there's some non-zero coupling between your chains, there's some temperature at which your correlation length diverges. And this is where long-range magnetic order sets in. But if you look at the quantum correlation length instead, you find that this length scale is more or less insensitive to the thermal phase transition. Nothing happens, but it's very strongly sensitive to how close you are to the ideal limit of the decoupled spin chains, the 1D Heisenberg limit. So what this is telling us is that these quantum correlations are insensitive to thermal phase transitions, but strongly sensitive to quantum phase transitions. And so a lot of people often ask me, like, what's the difference between just correlations and entanglement as you're measuring it? And I think this exercise makes it very clear. So The third answer, Q dependence of QFI encodes what we're calling a quantum correlation length. And this is sort of us building some intuition for how to interpret QFI in its momentum dependence. But now let me get on to maybe the most intriguing part of this talk. We look at some semi-classical examples where we use the field theory of magnons to describe some interacting spin systems and ask, what does this tell us about entanglement? So let's begin with a very trivial example, a uniform ferromagnet. This is something that you can write down in just a few lines with a derivation of spin wave theory. If you have all your spins polarized along the z direction, your inelastic neutron structure factor is given by this equation, 1/4 times this delta function where omega q is your dispersion. And it looks like this. You have some quadratic dispersion, but the intensity is equal across the entire Berlin zone if you have a uniform ferromagnet. If you go and calculate your quantum Fisher information along the x direction, there's no elastic scattering. Your SXX is 1/4 everywhere, 4 times 1/4 equals 1. Your entanglement depth is 1. There's no entanglement in the system, which makes sense because ferromagnets are product states. There should be no entanglement, and indeed in this exercise we find QFI witnesses no entanglement. So this is for ferromagnets. Antiferromagnets, however, do have intensity concentrated around certain wave vectors. So for example, the 2D square lattice antiferromagnet, this is another system that you can write down in closed form, the Magnon theory. It's not too hard. It takes a few pages of derivation, but you find that there is intensity, a diverging intensity at the ordering wave vector for this system. And being a little more formal about this, if your system has a small gap, you have peaked intensity, but as your gap goes to 0, your intensity actually goes to infinity. And this is called the infrared divergence of the 2D square lattice model. Divergent intensity implies a divergent QFI as you integrate over this intensity. And so your entanglement depth actually goes to infinity. And with a very small gap, you can get entanglement depth in the thousands very easily. So what's going on? Why is this semi-classical model so highly entangled? Well, I want to credit my postdoc, Wolfgang Simeth, for figuring this one out. What's going on, you have to go down to the Bogoliubov transform, because the antiferromagnet is actually not diagonal in the Nail basis. You have to apply the Bogoliubov transform to matrix rotate your state to diagonalize it, right? And the matrix rotation depends on your wave vector. And at the ordering wave vector, there's a 1/omega term in this. And if your system is gapless, then your Bogoliubov transform also diverges. Now, entanglement is a basis-dependent quantity, nowhere close to diagonal. This implies a very strongly entangled state. So the moral of the story is we shouldn't be distracted by the fact that we have this closed-form field theory that we can use to calculate the effects. The antiferromagnet is actually a very highly entangled state of matter. And things get even more interesting because this 2D square lattice antiferromagnet, we can tune it through a quantum phase transition and watch what happens. When we add a second neighbor exchange, to this model, exactly 1.5 zero magnetic order. And then if we calculate what happens on these semi-classics, we find that QFI goes, and in between these two states, QFI entanglement diverging over a whole continuous range of wave vectors. This is where an emergent size for the 2D triangular lattice, which also has a quantum phase boundary in the classical model at the second neighbor equals 1/8 of J1. And the same situation appears. QFI goes to infinity along a line of reciprocal space at this phase boundary. And this is precisely where in the quantum limit you have this finite region of a quantum spin liquid that shows up. Yes, question. This is all from semi-classical theory. No. So that's important. We're driving this field theory, outside this kind of range of stability. We know that in the real quantum limit, the Magnon picture completely breaks down and you get this emergent quantum phase. But in a sort of worldview of this semi-classical model, what happens that kind of is a harbinger of what this is telling us is that there's a diverging entanglement over a line of reciprocal space. And of course, the theory really breaks down But what it's telling us is that if the theory were valid, then entanglement would just go through the roof at a variety of wave vectors. But I want to emphasize that not all quantum phase transitions have diverging entanglement. So as an interesting counterexample, we can take a cubic ferromagnet where the ferromagnetic order is constrained to be along the 6 axes of a cube, and we put along a 1-1 magnetic field. At a certain field, we get a quantum phase boundary where it goes from a ferromagnetic state to a field polarized state. There's a sharp phase transition there, but it's a first order phase boundary, and there's nothing interesting whatsoever that shows up in the entanglement. Entanglement depth is 1 below, and entanglement depth is 1 above. This is just to emphasize that I think it's interesting that QFI seems to be able to distinguish interesting quantum phase transitions where there's some emergent physics, perhaps some quantum criticality, from boring quantum phase transitions where nothing interesting happens at all. Right. And so we tried this on a variety of models. We did it on the square lattice, the triangular lattice, the Pyrochlore lattice, the Kitaev model. And every time there's an emergent phase and Magnon breakdown, the semi-classical QFI diverges along a region of reciprocal space, which I think is very interesting. Now, as I already emphasized, this is not realistic. In real quantum limit, the Magnon picture breaks down. But I think it's interesting that in the semi-classics, when you see the entanglement start to diverge and go through the roof, you're entering regions where the magnons are strongly interacting, the quasi-particle breaks down, quasi-particle picture breaks down, and even you get some emergent phase where the divergence goes to infinity. So we're not the first ones to have pointed this out. Many theoretical studies have already kind of associated diverging QFI to quantum criticality. This was done in the original paper by HOQE in 2016. They looked at the transverse field easing model. This has also been shown by the Kitaev chain model and the Kondo lattice model by Chi Miao and his group. So I go through all this because I think there's some lessons here about what QFI means in condensed matter. And to me, there's 3 lessons here. First, semi-classical models can have very large entanglement. The interacting magnons of an antiferromagnet, the antiferromagnet itself is a highly entangled non-trivial state of matter. It just happens that we have a field theory that we can use to solve it. Second, QFI probes the degree to which the diagonal basis differs from the K basis, where K is the ordering wave vector. And third, diverging QFI is a witness of quasi-particle breakdown and emergent phases. So with that, I think I've used up my time. Let me put up my summary where the 4 conclusions I came to. First, QFI measures the degree of quantum superposition in your state. Second, the Q dependence of QFI carries information, and we need to think carefully about it. Third, semi-classical models can show very large, even diverging quantum entanglement. And fourth, diverging entanglement signals instabilities and emergent physics, such as quantum criticality. Now, there's much more to say. Please come talk to me if you want to know more, but I'll be happy to take any questions. That is found in the 6-point correlators around the loops of the honeycomb. And on the 2-point correlator limit, the correlation length is just 1 spin. So interesting in the Kitaev spin liquid in either the clean limit liquids, for example, the 2D gives some distinguishing feature from some quantum features kind of spin liquid.
What? The bonds and it'll be different or what?
Yes. So Nick Shannon has a paper on the archive where he explored this in the 2D triangular lattice, and they found that the temperature's dependence of QFI is actually an important quantity to look at. Because in the clean limit, it follows a power law, but that's a very sharp they see.
So just to follow up, maybe you already answered, that was the last statement. So if I have a boring antiferromagnetic correlated system, disorder smears the calculation, which says.
I mean, yes, it will definitely be smaller because the features will be smeared out in momentum because you've lost translational symmetry. So
would be
for the old paper by HOQE and folks who studied the transverse field-Ising model
Mhm.
versus the 3D case that you mentioned where the ferromagnet transition happens.
Yes.
Both are sort of similar phase transition. So what is the difference? Why do you see different?
Yeah, I'm going to confess I don't have some deep understanding of why the phase boundary and the cubic ferromag some people in this room understand.